Okay, we're recording now. Hello, hello. We're back to sets and functions. Let me go to my slides. Okay. I believe this is where we were last time. We said that operations on set operations. So first, in a sense, like first operation that we looked at is the subset relation between sets. Okay, it's not an operation exactly. It's just it's a relation on sets. So T is a subset of S if the following expression is true. For every X, if X is an element in set T, then it must follow that X is also an element of an S. So therefore, subset relation represents an implication between two predicates that X is in T implies that X is in S, and that implication must hold for all X. And this is much shorter way to write this relation between predicates. We didn't say this last time. There is a notion, it's called the proper subset, and it's denoted with just like this symbol. This symbol really means that it's a subset or it is equal. So this symbol kind of came from this one. Okay. Which simply means that T is a subset, but also it can be equal to S, right? Because in particular, if T and S are the same sets, this implication is true, right? It's a triviality. If X is in set T, then X is in set T. It always works. So therefore, if T and S are the same sets, you can always write this relation between them. But if T is a proper subset of sorry, this is a type of T, which is denoted T, this symbol S. So that is even only if T is a subset and they're not equal. Okay, let me maybe clear this. Sorry, this creates some mess for you, but hopefully we can recover from that relatively quickly. Okay, maybe not as quickly because now I lost the presentation. Why can't I click that? I don't know. Okay. Sorry. Okay, I will guess it's a lesson for me not to attempt to fix stuff in slides. Okay. Okay, so that was probably not worth it. Sorry about that. Okay, and now we have noise outside, sorry. Okay. All right. So that's the relation proper subset. Okay, and some examples, we went over them last time. Set operations correspond to other logical expressions on predicates which define the set. So for example, if you want to say that something is an element of A or an element of B, there is a very short formula for this. You say that this is an element of a union of the two sets, which expresses this formula in a shortened way. Okay, so it corresponds to all elements which belong to either set A or set B. Intersection, if you want to say that something is an element of set A and it's an element of set B, you just say it's an element of an intersection, which corresponds to this region. Oh, my pointer is off. Okay, now to this region. If you want to say that something is an element of A and not of B, then you write it using a set difference and notational remark the book denotes set difference with the same arithmetic sign of minus that is used for arithmetic difference. And if you want to say that X is not an element of A, you can express this using a complement symbol. So A complement is a set of all elements which satisfy this predicate. In other words, they do not satisfy whatever predicate that defines set F, A. Because complement means that well, you have to have some notion of the implicit universe to define a complement set properly. Like, for example, here we sort of restrict the environment universe to this blue box. Okay, let's do some examples. Here we have a short cheat sheet with basically all the logical, I mean, all the set operations we have introduced, which correspond to different logical Boolean expressions involving belong to either set A or to set B, where this is not, as I said, this is not a proper, it's not an operation. It's a relation between set. This is either true or false, depending whether this implication is true. And I'm missing the for all X sign right here. I will add this later. Okay, let's do some examples. Let's say A is a set of, here is a set builder notation, set of all x's in the among integers. In other words, integer x's such that these x's are also odd. In other words, A is a set of odd integers. B is another set builder instance. All x's who are integers, all integers, such that those integers are strictly greater than 0 and strictly less than 10. Okay, well, there is 9 integers like that, right? From 1, 2, 3, 4 to 9. C is just a roster notation. It's a set of 4 elements from 4, 5, 6, 7. Okay, and assume the universe is just in its integers, right? In fact, if I didn't specify it, this is what you should be assuming, because everything is in terms of integers. So sort of, if somebody does a complement later on, your assumption should be that the universe is in integers. Okay, so let's see, what is an intersection of A and B? Intersection of A and B is composed of all x's which satisfies this conjunction. It's an x which is in both A and it's also in B. So let's show what kind of x's satisfy. X is those integers that satisfy this predicate. B is all integers that satisfy this predicate. So conjunction, of course, means must satisfy both this and that predicate. So it's, in other words, it's an odd integer between 0 and 10. So it's 1, 3, 5, 7, 9, right? Let's look at what about intersection of C and a complement of A? So, okay, again, Boolean formula for intersection is that it has to be in the first set and in the second. In this case, it has to be in C. So it's a very restricted choice. It's only 4 possibilities. And also must be in a complement of A. Somebody is in a complement of A if they're not in A. So which of these guys here is not in A? A is a set of odd integers. Its complement is therefore a set of even integers, right? They are complementary, odds and evens. So even. So well, So it must belong to 4, 5, 6, 7 and be even. So it's 4 and 6 only, right? Let's check whether C is a subset of B. Is it true that for all X missing here, if X is in C, then X is in B? Okay, so that formula is interesting only if X is indeed in C. So let's instantiate it for X equals 4, 5, 6, and 7. And is it true that for all those X's, X is in this set? And yes, it is true, right? Because these are all integers, such that all these integers are indeed between 0 and 10. So this is a yes. What about B as a subset of A? Well, no. So if you're trying to do the same implication, for every element of B, is it also an element of A? So is it true that for every element here, they are all odd? Well, of course they're not, right? You have 2, 4, 6, and 8, which are not in A. So therefore, this statement is false. So 2 is a counterexample, but so is 4, so is 6, so is 8. What about the complement of a union of A and C? Okay, what on earth is this? Okay, so these are what's a union? It has to be in either one set or the other. So it's either odd or it's 4, 5, 6, 7. Okay, well, 5 and 7 are sort of defined double because they're both odd and in here. So the union of A and C is odd plus what comes new in here? Well, 4 and 6. So it's just odd integers, and in addition, there's a 4 and 6. Now, if you complement it, what do you get? Well, actually, we don't have to specify everything that you get. We are only asked, is 6 in the complement? But to be in the complement, you have to be not in the set, as we just said. 6 is in the set, right? Because it's a union of C and A. 6 is in C, therefore it's in the union, therefore it is not in the complement of that union. Okay. What about 26? And 26 is, okay, when is somebody inside of a complement of a union? Okay, so they must not belong to a union, which belonging to a union means that you either are in first or in the second. So if you negate conjunction, what do you get? We were saying somebody is in the complement of a union when it is not the case that they're either in the first or the second. So it's a negation of a conjunction. What's the negation of a conjunction? It's a disjunction, sorry, negation. So it's a conjunction of two negations. He's not in the first and he's not in the second. Yes, that's the only way, right? He can be not in the union. He's not in the first and he's not in the second. Let's test. 26 is not in the first set and it's not in the second. Therefore, he is in the complement of their union. Okay. Okay, it's just some examples, right? Like we can do more, and of course you should do more. There is some in homework. There is additional exercises. You should do it until you think that you can do this type of stuff. Okay, so like you can wake up and you're given some formula and like you can actually reason, yeah, you're sure it's no, it's a complement of a union of an intersection. Okay, so you know, you have to do it. Power set. So another concept. But you know, some sort of nirvana should you know, settle in as you, for example, because operations on sets are like one-to-one to Boolean formulas. So if you achieve some sort of quasi-nirvana understanding Boolean formulas and being able to reason about them, then the same stuff should now reappear. And one thing should you know, strengthen the other. It's sort of the same thing in a different guise. Power set. Power set is a concept. If A is a finite set, then power set of A is denoted P of A in brackets, and what it stands for is the set of all subsets of A. Let's look at an example. Let's say A is a set of just 3 elements, A, B, C. How many different subsets does this set A have? It has 8 different subsets. So first of all, an empty set is a subset of A. Let's test. Is it true that if X is in this thing, then X is in A? Yes, it is true, because there is no X which is in this thing. This is an empty set. It does not contain any element. So the implication that says if X is in here, then X is in here is true. Therefore, empty set is a subset of A. Of course, this argument goes for any set A, right? It has nothing to do with set A. Empty set is a subset of everything. Another set that is a subset of A is a set that whose only element is A, little a, right? Again, is it true that for all elements in this set, call them X, they also belong to this set? And rather immediately, it is true. The only element that belongs to this set is A, and that guy is in this set. The same convinces you that this set and this set are also subsets of this. These sets have a special name. They're called singletons. It's a set who has only one element. It is not a supernatural notion, right? Because, like, you know, if I say, you know, there is a set of people in the room, and it's only one person in the room, you know, like in my room now, or sadly, in probably many of our rooms right now, right? There is a set of people in your room. It's a one person, yeah, but it is a set. And, you know, from a computer science point of view, it is very crucial to see that there is a difference between a variable that whose value can be an integer, and a variable whose value is a list, but that list has only one integer in it. These are different types. You know, you would have different data structures to represent them. To represent an integer that is between 0 and 256, you need a byte. To represent sets, you need some other data structure, for example, a linked list. And, well, it might so happen that the linked list, when you initialize it, for example, is empty. So it's an empty set. Perhaps after the first insert, there is only one element in that set, but it's a different data structure than just, you know, a set of integers. Even if it has a single integer in it, you would use a different data structure to represent it. You can maybe think that way of, like, when you say, okay, what on earth is a set whose only element is just little guy A, you know, and how different is it from just that little guy A? These are more natural subsets, right? Like, in a sense, right? Because they at least have 2 elements. And then here is the complete subset, right? Like the full subset, which is in fact the whole set A. And because subset relation includes A is a subset of A, right? Because for every X in A, X is also in A. So this is a test. A is a subset of A, right? Here is an example. This is set capital A, right? Which is a subset of itself. All these subsets are called proper subsets. This one is not. So a proper subset of a set is any subset which is not the set itself. Okay. Okay. There is eight of these subsets. When you start making subsets, you will sort of see that a power set, the number of elements in the power set is always a power of 2. Okay, and okay, you can sort of pause for a moment and sort of think why. Okay, but we will come back to it. And as a computer engineer, you will come back to it many times. So is A and B an element of the power set? In other words, well, that is the same to say, is the set containing A and B a subset of this set? And yes, it is. We list it here. Okay. To be an element in the power set is an even only if this thing is a subset of A, right? Because the power set is the set that contains all subset of A. So when is something a member of the power set? If that something is a subset of A. Is this a subset of A? Yes. Okay, how about this? Is this set a subset of the power set? Let's test. What does it mean that the thing on the left is a subset on the thing on the right? Is it true that for every X that belongs to this, that X belongs to here? Let's instantiate X. Let's make X little a. It belongs to this left-hand side subset, right? Does little a belong to here? No, it doesn't. What belongs to here is different sets, whose little a is an element of, but little a itself does not belong to this set. It's a no. Okay, so again, if if A is an integer is not a set of integers. Okay, this is the same question: is little a element of the power set? And no, and we already said that. What about a singleton set whose only element is a little a? Well, that guy now is a member of the power set. It is listed here. How about moving a level of abstraction up? How about a set whose only element is a set whose only element is little a? So, okay, so it's like you have a thinking data structure, you have a data structure which is sets of sets. Okay, is this a subset of the power set? Okay, let's test. Is it true that for every X, if X is an element of the left-hand side, then X is an element of the right-hand side? What is the only X which is an element of the left-hand side? X is this singleton set. It's the set whose only element is A. So this is my X. This set. Is X an element of the power set? Well, here is the power set in a roster notation, and that singleton set is found there. It's a yes. Okay, in fact, it's just by this, right? We already established that this singleton set is an element of the power set, and that allows you to conclude that it's true as well. What about an empty set? Is it a subset? Empty set is a subset of everything, because the implication, if X belongs to the left-hand side, then it belongs to the right-hand side, works always. It's nothing is an element of the left-hand side, therefore the implication is always true. What about, is an empty set a member of the power set? Well, actually it is, right? So it's the same symbol. It is both a subset and an element. Anyway, it's probably the only thing for which this works. Okay, it is. You can ask, like, why this kind of mental torture? I mean, it's just so you distinguish between a set versus its element and a set of sets, and what is a membership and what is a subset. Okay, that's all. Okay. While sets were unordered data structures. Okay, so a set has no order. You either belong to a set or you don't belong to a set. There is no notion of first, second, third member of a set. But that's not often all that we need. Sometimes we want to have lists where elements are ordered, and they are, also important to express stuff around us. So the simplest list is a list of two elements, an ordered pair, and we designate them with round brackets, which, by contrast to the, form a visual contrast with curly brackets that indicate sets. And we use open brackets to designate lists. The only difference is that in lists order matters, and in sets it does not. So, for example, a set which contains element A, B listed in this order is the same as the set containing B and A listed in that order. But a sequence of two elements with the round bracket is not the same thing as the sequence of the same two elements, but in a different order. Well, we can have sequence of three elements, a triplet. And because it's an ordered object, it makes sense to say, for example, that B is the second element of this ordered sequence. Whereas for a set, it would not make sense. Of course, you can have 4 tuples, 5 tuples. In general, you can have lists of arbitrary length, and they are called sequences. Okay, so we are going to use list is another word, but we'll call them sequence one more time. Oh, somebody says, can I explain 2 one more time? And I don't know whether this referred to something on this slide or yes, you mean this one? Why this is not a subset? Because of this. Look, little a is not a member of the power set. It's not here. A singleton set whose only member is a is a subset, but little a itself is not. So number 3, the fact that this is false implies that this is false, right? Because if you know what a subset means, it means every element who is an element of this set must be a member of this. Well, even the first one, it fails. Actually, for the second one, it will fail as well. Okay, it's arbitrary difference. Yeah. Power set is a set of sets. Every element of a power set is a set, right? Because a subset is a set. little a is not a set. Okay, so just it's not a member of the power set. Power set is a set of sets. Of course, not all sets, right? Only subsets of A. But first of all, they have to be sets. Okay, so we have these ordered data structures now, the sequences. Sequences are related to a concept called product between sets, Cartesian product. Let S and T be sets. Cartesian product of sets S and set T is denoted with like a kind of a product sign, which sometimes in arithmetics you designate multiplication using this symbol. But now you multiply two sets. What does this stand for? Cartesian product of set S and set T is a product, it's a set of two element sequences, in other words, pairs, whose first element is a subset of S, is an element of S, and second element is an element of T. In other words, this Cartesian product of S and T is a set of pairs whose first element is in S and second element is in T. Okay, let's do an example. Let's take, let S be a set of three letters, A, B, C, and T set of two integers, 1, 2. What is a Cartesian product of a set of three letters, A, B, C, and two digits, 1, 2? It's a set of all pairs whose first element is a member here, so it's A, B, or C, and the second element is a digit, is a member of here, of T, so it's a digit either 1 or 2. So here are all these pairs: A1, A2, B1, B2, C1, C2. Yes. You can see how this would be useful in in a data structure, right? You have a set of students, a set of classes that a set of say classes they take, right? And what's the Cartesian product? Is pairs of student class. Okay. Here is a Cartesian product. Okay, another example. Let's say that it's can we take a Cartesian product of a set with itself? Yes, it is actually denoted using the power notation. Just like in arithmetics, when you multiply T by itself, that's called squaring. So if T is this set of two digits, 1, 2, what is this Cartesian product? It's a set of all sequences of all pairs whose first element is either 1, 2, either 1 or 2, and the second element is also either 1 or 2. Okay, so there's let's do some tests on this. Is T a subset of the Cartesian product of T and itself? No, because syntactically these are different objects. This is a set of integers. Okay, restricted, very restricted, of only these two integers. This is a set of pairs. This is the set of sequences of length 2. They're just syntactically different objects. Okay, so nothing in here is also in here, because nothing in here, everything here is an integer, everything here is a sequence of integers, and that's a mismatch. What is R square? So a Cartesian product of reals with reals. Okay, pairs of real numbers, right? Like, for example, pairs on a plane can be designated as R square times R square. This defines you a plane. What is Z square? Z was integers. This pair of integers. So on a plane, if we draw a lattice along, the integer, all the integer intervals, and make dots on them, these will be pairs of integers. So here is a computer science example. Let's say you want a data structure where you have two types of drinks, orange juice, coffee, three types of main dishes, waffles, eggs, pancakes, two side dishes, hash brown and toast. A selection of a dish is a member of the Cartesian product of drink, main dish, and side dish. So for example, orange juice, eggs, and toast is a member of this Cartesian product. It's a sequence whose first element is element of the first set, second is an element of the second set, third element of the third set, right? So this is indeed a set of all triples whose first element is in here, second in here, third in here. A very natural use of these, you can think in in a data structure. In general, if AIs are sets, then I can take the Cartesian product of all of them. And what would that represent? It would represent all sequence of length n, whose first elements are in this set, the second element are in this set, etc. In other words, the ith element of this sequence is an element of the ith set. Okay, so the first element in the first set, second in second, etc. This is a set builder notation, right? This is a set of sequences of length n, such that I designate these sequences by x1, x2, to xn. The xith element is a member of aith set. Okay. Okay. So, for example, what is S to the n? So, a Cartesian product of some set with itself. It's a very short form, designates all sequences of elements of length n, whose first element is a set of S, and second, and third, etc. So these are all sequences over set S of length n. Okay, that's what it designates. So for example, if my set is bits, what's bits to the third? It is a Cartesian product of bits cross bits cross bits. So this designates triples of bits, sequences of length 3, whose first element is a bit, 0, 1, second element a bit, 0, 1, third element a bit. You can see that we would in stating like what are the inputs to a program, what are the outputs of some procedure, this would be very good things to have. If I want to say my inputs are letters, sequences of letters up to length 10, okay, then I can say all x's that are entered into this program must be members of set of letters to the 10. Okay. R4, what is this? It's a Cartesian product of R with itself 4 times. In other words, 4 tuples of reals. So length 4 sequences whose members are reals. Okay, and if I tell you that, like, whatever piece of code I wrote takes inputs in this domain, then oh, okay, these are they're supposed to be 4 tuples of reals. If I told you that in this domain, then that these are triples of bits. Very different objects I should feed these 2 pieces of code. If sigma is a set of some characters, for example, bits or letters or numerical digits, okay, then sigma to the n stands for n long sequences The first element is in sigma, second in sigma, third in sigma, etc., right? But so I should write them with first element, comma, second, comma, third, comma, fourth. But if I wanted to describe bit strings this way, it is not super convenient to put commas in between every bit. So I'll very typically not do that and represent a bit string as a sequence without putting commas. So this is an example. My sigma contains only two elements, 0 and 1. The sigma is bits. Sigma to the third is set of binary strings of length 3. Instead of representing them in this form, sequences of length 3, 0, 0, 0, next sequence, 0, 0, 1, I would just concatenate them, right? Because this is indeed a typical representation of a bit string that we all use and love. If the only times that you should use this notation, open bracket, close bracket, and commas in between, is if the characters in the set over which this is a sequence are in some sense ambiguous, right? Like, so for example, if this is a set over integers, then you better put commas, because if you write a string 111, I don't know whether that denotes 11 as the first element, comma 1 as the second, or perhaps it's a single element 111. That's also an integer. So this can be only done if your sigma is made of distinct characters, right? Like, for example, your sigma is just bits or decimal integers from 0 to 9, or letters of the English alphabet, which are all distinct. So now, if you think of sequences as strings, okay, so in other words, this is a sequence and 4 tuple, and this is the same sequence, but basically represented as a string. Okay, so I didn't say what a string is, but it is a string of an alphabet is a sequence whose elements are members of this alphabet. Okay, but they're just visually represented, not in the sequence notation, but just concatenating all these characters together. So this notion of concatenation can apply not just to individual characters in a string, but to strings themselves. So let's say you have a string abba, okay, over this character, over this alphabet, who contains just 2 characters, A and B. And you can concatenate it to another string over the same alphabet, and we denote the concatenation in this incredibly simplistic way. Just write 2 variables one after another. If X is a string and Y is a string, then writing them this way one after another represents concatenation of these 2 strings, which would be this string. You can one of these strings could be just a single character. For example, this is the case where Y is A. So concatenating X and Y would give you this string, right? This notation, if you know that these are strings, then you know that these writing them this way represent concatenation. But sometimes, maybe you overlooked, it's not clear, maybe it was, defined 5 pages back, and you don't know that what does this represent? Are these integers? And perhaps this stands for multiplication of integers, or are these strings? And this string stands for concatenation. So we do sometimes use this symbol, vertical bar, to designate concatenation as well. Now, a few slides back, I used the vertical bar to denote cardinality of a set. Okay, unfortunately, that's true. Like the same symbols are used in different contexts for different things. Just like putting two symbols like this together might represent multiplication if these are elements, say, if these are numbers, but it will also stand for concatenation if these things are strings. Just like an empty set, there is also a special notation for an empty string, which is, even though in some sense it's a nonsensical object, who needs just like a zero is okay, who needs a zero? Why do you need zero when you count? Well, it is convenient. Likewise, it's convenient to have a special symbol for an empty string. In particular, if you take any string and concatenate an empty one to it, you're getting the same string, whether you can concatenate empty string in the back or in the front. The vertical bars, just to pile, another notation which reuses the same symbols in yet another way, can represent a length of a string. So if X is a string, then these vertical bars around it would represent its length. For example, if X is up bar, then putting the bars, the length of the string is 4. Okay, that's basically a third way of using vertical, right? If you knew that X is a set, this stands for cardinality of the set. If you know that X is a string, then the exact same notation stands for length of that string. Okay, now here I have the little cheat sheet with the 3 notions of where we use vertical bars so far. The sets of string can be infinite. So there is a special, sigma to the, sigma to the 2. What was this? This was a Cartesian product of sigma with itself. In other words, set of pairs whose first element is in sigma, second in sigma. In other words, set of strings of length 2, both of them in sigma. Now, this is a set of just elements of sigma. So these are also strings over the sigma alphabet, but with just one element in it, right? Like, so it's a strings of length 1. I can have sigma to the 3rd, which is strings of length 3, and then union sigma to the 4th, strings of length 4. What is sigma to the 0? It's an empty string. Okay, these are strings over the alphabet sigma of length 0. There is only one string of length 0. It's an empty string, regardless of the alphabet. If I want to say that I have a string over alphabet sigma, think of sigma as bits. It just has 2 elements, sigma, 0 and 1. This is the empty bit strings. This is the bit strings of length 1, bit strings of length 2, bit strings of length 3. If I want to say that my input is any bit string, I don't need to say how long. I have a symbol for it. It's sigma to the star. Okay, this stands for this infinite union of all 0 length strings, 1 length strings, 2 length strings, 3 length strings, arbitrary length strings. So what is the sigma is the bits star. These guys, which is only one element, empty string. These guys are length 1 bit strings, so 0 and 1. These guys are all these 4 length 2 bit strings, and the next is too much to write, like three length bit strings, 4 length bit strings. Okay. So it's a shortened notation for this infinite union of all these fixed length strings. There is also less used, but an element set to the plus. It is the same as this, but except that you kick out the empty string. Okay, just like from the notation for positive integers. It's all integers, I mean, positive naturals and plus. It's all except you kick out the 0. Okay. So, there's a little bit of a mouthful, but, once you sort of acquaint yourself, and it starts being natural that sigma to the k is strings of length k over alphabet sigma, then it's very natural to express the set of all strings over alphabet sigma, no matter how long. So anything that belongs here is some string of some length over sigma. Okay, so you pick a string in here, it has some length. It does belong to one of these sets. Okay, namely the one, defined by the length of that particular one, right? Okay. That's all I'm going to say in lectures about sets. We'll be coming back to them, and we'll use them over and over and over. You should do the exercises. You should make sure that you understand these things, and the book will have additional examples and additional sort of taking material in putting a giving you extra food for thought, basically. But I'm moving to functions. A function is, of course, you've seen functions in earlier schools, right? So, but let's revisit what a function is. It's a map between two sets called domain and a target set. Sometimes the target set is also called the codomain. And it's also popular to call this a range, but technically I would define a range slightly differently, namely as a subset of the codomain for which that is in some sense really used by function f. Okay, so there will be a technical difference between what a range is. Okay, the map means that every element in the domain, its value under function f must be defined, and it must be defined. Okay, must be defined for every element, must be defined uniquely. It cannot be that this map somehow maps the same element to different ones, and its value must be in the set. Okay, if any of these constraints are not satisfied, then this is not a function. It is not a successful definition of some map between the domain A and codomain B. Here is a successful definition of a map between domain ABCD and codomain 1, 2, 3, 4, 5, because it defines a value for every element in the domain, and it defines it uniquely. So A is mapped to 1, B to 4, C to 2, D to 4, there is no ambiguity about what is the value of that the function f maps element b to. And all the values are indeed in this codomain. Okay, so the fact that some values are not mapped by anyone, and that some values are mapped by more than one argument is not a problem. It is a function. It is a well-defined function. The range is those elements in the codomain for whom there exists element x such that f of x equals that value. This if x for y is something called pre-image. So a pre-image of 2 in function f exists, and it's C. Pre-image of 3 does not exist. So therefore 3 is not in the range. Pre-image of 4 exists, and actually it's a set of pre-images. It has 2 elements, B and D, in it. Therefore, that's fine, and 4 is an element of the range. So in other words, the range is always a subset of the codomain, but it could be the complete subset. In other words, right? It's not always a proper subset. The range could equal codomain. So functions arithmetic functions can be specified by some arithmetic formula. So, for example, a function from real to real is by a polynomial of second degree, right? F of x, f maps every element, real element of x, which is an element of R, into some other element of R, namely x squared minus 4x plus 3. And you can check that, you know, whatever for every real, this thing is some real number. Therefore, it's in here, and it's always defined. There is never, there is no real for which this is not a real number, and it's unique, right? There is only one number that this expresses. But here are examples of expressions which fail to define functions. For example, f of x is plus minus square root of x. So this fails to define a function for many reasons. Like, for example, f of 4, okay, there is a square root of 4, right? It's the 2. But f of x is as if it was both plus 2 and minus 2, and that violates the non-ambiguity requirement on what a map is. Every element has to be mapped to one value and not 2. Moreover, for negative values, right, the square root is not defined at all. Likewise, this is not a successful map from reals to reals. There is one problem with it, namely for x equal to 0, it fails to define anything because 2 divided by 0 is not clear. Well, it's an undefined symbol, and it's not a real number. Now, these properties of functions, sometimes that they have collisions, namely 2 elements mapped to the same, and also that they might miss some element in the codomain. These properties have names, and they are useful in characterizing functions. So one such characterization is you call a function one-to-one or an injection if it has property that no 2 elements in the domain are mapped to the same element. In other words, the following implication must be true. For any 2 elements in the domain, if they are different, then the function f will map them to different elements in the codomain. This is not a one-to-one function because this implication is going to fail for x equal b and x prime equal d, right? B and d are 2 different elements, but function f maps them to the same values. Therefore, this part is false. So the implication is not true. And B and D are indeed the only counterexample for this implication, right? But it is in the counterexample. The function is not one-to-one. This behavior that two elements are mapped to the same value is called collision in a function, right? Like, so it's very common in data structures. Like, for example, think of hash function. You hashing your data, and you putting it in a box in a hash table based on the value that the hash function gives to this object. If there's two different objects which are put in the same hash table, well, that's because the hash function collided on these two objects. It computed the same table index on two different values. This function is, however, one-to-one, right? Because you can see visually there is no collisions. There is no value that has more than two pre-images. That's exactly another way to define one-to-one function, right? It's that no argument has no element in the codomain has more than one pre-image. It might have 0 pre-images, but it might have 1, but it cannot have more than 1. Okay. Some examples of one-to-one functions. Okay, is this function one-to-one from reals to reals? F of x is x squared. No, it's not. There is collisions. For example, 1 and -1 form a collision. 1 square and -1 square are the same thing as 1, right? In fact, every x and -x forms a collision in this function. What about a linear function? So 2x plus 3, and my domain and codomain are integers. Well, is it a well-defined function? Yes. And is this, if an argument is an integer, is this value always an integer? Yes, it is. So it is a function from integers to integers, and it has no collisions, right? If 2x plus 3 equals 2x prime plus 3, then x equals x prime. So the only way two values are equal if the arguments are the same, and therefore there's no collisions. What about a function on bit strings of length 3, which outputs from length 3 bit strings to length 3 bit strings? The function is defined like this. I take the input length 3 bit string, and I replace the last bit in it with a 0. So for example, if my input bit string is 111, the result of this action would be to replace the last bit here with a 0. So this function maps 111 bit string into 110, right? Thus, this function is well defined. Every length 3 bit string, when you perform this action on it, what do you get? A 3-length bit string of some sort. Namely, okay, particularly, it will always have a 0 at the end, but it is a 3-length bit string, so it's in here. Is it a function? Does it have collisions? Yes, it has collisions. If you take 2 bit strings, which are the same everywhere except the last bit, then this function will collide them, right? Because replacing the last bit here with a 0 and replacing the last bit here with a 0 gives you the same string, this one. Okay, and there's many other counterexamples, right? Like any 2 strings that have the same first 2 bits. What about this function again on bits? The inputs are length 3 bit strings, the outputs are length 4 bit strings, and what the function does is it takes its input bit string and it adds a 0 to it. So for example, if the input is 101, the output is 1010. 1010, right? Does it have collisions? No. Well, it's a well-defined function, right? It indeed goes from 3 bits to 4 bits. And it cannot collide, because if you have f of x, let's say that f of x equal f of y, or f of x equal f of x prime. What is f of x? It's x with n a 0. So it's x0. What is f of x prime? It's x prime 0. If x0 equals x prime 0 as bit strings, the only way that can happen is if x and x prime are the same, right? So no collision. What about this? It's a function that takes a power set and outputs an integer. So the inputs to the function are subsets of set A. That's the domain. It's the power set of A. In other words, all subsets of A. And the outputs are integers. And what's the function? To set, we map the set to its cardinality. So it's good, right? The outputs are integers because cardinality of a set is an integer. So it's always in here, and it's always well defined. Every set has a fixed cardinality, so it is a good function. Does it have collisions? Yeah, plenty, right? Every singleton is going to be mapped to the same integer, 1. And every 2-element subset is mapped to 2, and every 3-element subset is mapped to 3. 3-element subset does not form a collision because there is only 1. Empty subset does not create collision because it's only 1, but all the other form collision. Okay, a converse notion in some sense, okay, is an onto. It's a function that is onto. So it's a function that satisfies this predicate. For every element in the target, in the codomain, there exists an X in the domain that is mapped to it. In other words, every value in the codomain has a pre-image. It might have more than one, like this one has 2 pre-images, but it has some. So for example, this function fails this predicate. 3 is a counterexample. It does not have any pre-image. In other words, there exists, if I instantiate y with a 3, then this statement is false. There is no x in the domain such that f of x maps to 3. Okay, but for this, it is true. Yes, this predicate will hold. So, I mean, they're not exactly, so what I said is that one-to-one means that in terms of pre-image sizes, that every element in the codomain has perhaps the pre-image is 0. There is no pre-image. But if the pre-image is non-zero, then it's not empty. Then it contains only one element. What the onto means is that pre-images must be non-empty. Perhaps they must contain at least one element. So onto means that the pre-images of every element in the codomain, the pre-images are at least size 1. One-to-one meant that the pre-images are of size at most 1. Okay, so in that sense, they are complementary notions. So let's see some examples of onto functions. Okay, these are actually the same function. So like, is a squaring function onto over reals? No, it's not, because it cannot answer negative numbers, right? Like it will. So all the negative elements in the reals have no pre-images. They're not. There is no x such that x squared is a negative number. So this would be like this guy here, who's left out. Nobody maps to him. Yeah. So therefore, this square is not an onto function, and any negative number is a counterexample. Is this linear function onto integers? Okay, let's test. Is it true that for every integer y, there exists an x such that 2x plus 3 is y? Well, if you think like, no, because if it was on reals, then yes. For every real y, there exists a real x such that 2x plus 3 is y, right? It's just y minus 3 divided by 2. That's always divided. Over rationals, there's always, right? Because you can divide over rationals. Y minus 3 over 2 is some rational if y is rational. But y minus 3 over 2 is not necessarily an integer if y is an integer, right? So if y is odd, then y minus 3 over 2 is an integer. But if y is even, then y minus 3 over 2 is not an integer. Okay, so any even number would go as a counterexample. But over reals, this works. Okay, I'm missing here. Doesn't okay, so I guess I revealed my answers here. So let's see. Is this function that takes a 3-bit string and replaces the last bit with a 0? It was not one-to-one. Is it onto? Is every bit string producible using this rule? Take a bit string and replace the last bit with 0. No, not every bit string, because a bit string that ends with 1 will never be in the range of this function, right? So therefore, this function misses these. So it's not onto 3-bit strings. If I have a function that takes 3-length bit strings and output 2-length bit strings by simply dropping the last bit of a string. For example, on 101, it would output 10. Is it onto? Yes, it's onto, right? Because every 2-bit string can be produced using this rule. In fact, it always has 2 preimages. That string with a 0 attached to postfix with a 0, and that same string with 1 appended at the end, right? Dropping the last bit will map both of these guys back into the string. Well, here's some more complex. So let's say the function, what it does with the 3-bit string, it removes the, so you have three bits, okay? And you remove the last one and you put it at the beginning. Okay, sorry. So you remove the last one and you put it at the beginning. Okay, you always, when you start with 3 bits, you have a 3 bits, so it's a well-defined function. On a, you know, the range is proper. Is it an onto function? Yes, because take any bit string, and you can convince yourself that yes, there is a argument that will output that bit string. Is reverse the action, right? Put the first bit back into the beginning. That bit string will be mapped to the bit string you started with. So it is an onto. Everything has a pre-image in this one. There is a beautiful notion that captures both. It's called bijection. A function is a bijection if it's both one-to-one and onto. And in other words, if one-to-one, meaning it has no collisions, every argument, you know, it goes to, it's mapped to a distinct value. And it's onto, meaning that every element in the range is covered, in the codomain is covered. So in terms of pre-images, this means that every element in the codomain has at most one preimage, but also at least one preimage. And therefore, of course, the only way this both can be satisfied is every element codomain has exactly one preimage. So therefore, bijection means that the function is invertible, because everybody on the left is mapped to somebody on the right, but also the person on the right, every of them is mapped to a unique person back, right? It is mapped from a unique person, because the preimage for everyone in the codomain is non-zero, so it's mapped by someone, and also it is exactly one element. So you can define an inverse of a bijection. And one consequence of that is that if there is a bijection between set A and set B, therefore they must have the same cardinality, right? Because there is some one-to-one correspondence between elements in A and elements in the B, and this one-to-one correspondence is invertible, so it's a bijection. Therefore, these two sets have the same cardinality. In fact, this is commonly used to argue that are these two sets the same sets? You know, am I just looking at this? Is it a different way to count what in effect are the same classes of objects? If I can see bijection between these two classes, then this convinces me that yes, they are themselves the same class, because they have the same cardinality. There are two ways of looking at the same thing, if you will. I have some just a little notes that because cardinality is you can define this relation. Two sets have the same cardinality even if there is a bijection between them. You can also define it for infinite sets. So we don't know what this is because it's an infinity, but we say that two infinite sets have the same cardinality if there's a bijection between them. It is non-trivial because, for example, it turns out that the set of set of integers, which is naturals and negative, right? Which is naturals is positive integers and a zero. So integers have more elements in some sense, right? It's also integers, positive and negative. But in fact, they have the same cardinality because there is a bijection between them. Bijection is easy. There are many bijections you can show, but look at this one. I'm going to show you that there is a bijection between naturals and integers. Here is my bijection. Takes any natural number, 0, 1, 2, etc., and it assigns to that number n half of it if it's an even number, or it takes n plus 1 and halves it and puts a minus sign if it's an odd number. You can convince yourself that, look, if n is even, then this is an integer. If n is odd, then n plus 1 is even, therefore you can divide by 2, and this is going to be an integer, and it's going to be a negative integer. So you are always in this domain, in this codomain. And these are well defined. It's unique, right? A number is either even, and therefore the output is here, or it's odd, and the output is here. A number cannot be both even and odd. Okay, so this is unambiguous. Okay, so now look, what are the functions of this function on consecutive elements in domain? The first one is 0. It's an even, so 0 divided by 2 is a 0. So the function outputs 0. On 1, it's an odd. 1 plus 1 is 2 divided by 2, so that's 1 minus. So the value of the function is minus 1. On 2, it's an even. So 2 divided by 2 is 1. On 3, it's an odd. So 3 plus 1 is 4 divided by 2, 2 with a minus sign, so it's minus 2. And so forth it goes. You can see that on all evens, all even integers arguments, I'm going to have 0, 1, 2, 3, 4, etc. And all the odds, I'm going to have minus 1, minus 2, minus 3. So this function just kind of jumps around and says, you know, starts from 0 to minus 1, 1, minus 2, 2, minus 3, 3, minus 4, 4. And it eventually covers all integers, right? So you can see for any integer out there, there exists a pre-image, right? So take a million. Okay, what's the pre-image? It's 2 million. Take a minus million. What's the pre-image? It's 2 million and 1, or 2 million minus 1. They always exist. So there is a bijection. This actually shows that it's an illusion that there is more, in some sense, integers than naturals. These two sets have are bijected. Pairs of naturals are also the same as naturals. There is a bijection between them. And I can draw it for you, or you can look at the internet to find it. But, you know, if you basically cover all pairs with a line like this, sort of imagine a set of diagonal lines. You're putting all pairs of naturals on the string. And you can have a closed formula for this, right? It's not so hard to define. And again, you mapped integers to pairs of integers in a bijective way. Because rationals can be really thought of as a subset of pairs of integers, right? Like what is a rational number? Is 2 integers divided. It's a subset because 2 over 4 is the same as 4 over 8 or 3 over 6. But you know, if you kick out collisions, then because Q is a subset of n cross product n, so it's smaller in some sense, right? At most, I mean, at best. And if n cross product n has the same cardinality as n, then so is this smaller set. It's not really smaller because there is bijection between these as well. So turns out rationals have the same cardinality as naturals, but reals do not. So if you try to do this for reals, you can't. And we'll just see, because it's a beautiful thing. It's actually a very, you know, it's not hard and it's very deep. And it will reappear in your life, because it's the same proof that, okay, so you might not go into logic, that logic is incomplete, meaning that there is true statements that have no proofs. But also you will see this in terms of for computability, that there are some problems that have no Turing machine that can solve those problems. In other words, there are some problems that have no algorithm. It does not, an algorithm cannot exist that would solve a problem. It's actually a fundamentally very similar proof to show that. So here it is in a sort of easier guide. Okay, and we talked about inverses, so I have the final slide about inverses. So please have a look at that. I will end the lecture here. I have no slides I was going to go over. There's one more concept, at least in the book. It's about composition of functions. So you take a function and you compose it with another one. I will suggest to TAs to, you know, give enough examples for for inverses and compositions. There's some on the homework. There's of course more examples in the book. Okay, so I will end here. Sorry to go over. And I will stop recording, but you